Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is hydraulic schematics. Our objective is to examine schematic symbols used to represent common hydraulic devices, as well as discuss general schematic guidelines. Hydraulic schematics, quite like electrical schematics, make the task of representing the connection of those devices constituting a larger system easier, more efficient, and understandable. Consider three different methods of illustrating a directional control valve. The pictorial representation, while accurate, isn't easy to draw nor comprehend. The cutaway diagram, while detailed, is kind of confusing. The schematic symbol, in contrast, makes it possible to simply and efficiently represent the function even when employing directional control valves from entirely different manufacturers. If you've been following this playlist in its intended sequence, you should already be familiar with most of the schematic symbols we are about to discuss. This lecture therefore serves not necessarily as an introduction to schematics, but rather a review. If at any time you feel this lecture is over your head, by all means revisit and review the previous lectures. This lecture does, however, introduce some new devices on an introductory level. Later lectures will examine these devices in greater detail. Let's first establish some general guidelines regarding schematics. First, fluid conductors like hoses and pipes can be divided into three general categories. Primary or working, pilot, and drain passages. Primary or working fluid conductors are represented schematically as solid lines and used to conduct high pressure, high flow rate primary hydraulic power. These are the working lines that transmit fluid power. Pilot lines, in contrast, are represented schematically as dashed lines. These are sensory or control lines designed to carry low flow rate oil-based control signals. You'll often see pilot lines internal to another device's schematic symbol, giving you a clue as to which port is being monitored by the pilot passage. The pilot line on a pressure relief valve is a classic example. Alternatively, you might see pilot lines actuating pilot-operated directional control valves or pilot-operated check valves. Finally, drain lines are represented schematically as dotted lines. As the name implies, drain lines are used to keep a space clear of accumulated fluid. Ordinarily, drain lines are routed back to the reservoir. You'll often see drain lines in pressure control valves with pressurized secondary ports or sometimes the case drain of a pump or rotating coupling. Since dotted lines from all devices utilizing drains all routed to a single reservoir symbol would be confusing, you'll often see the dotted drain line ending in a tiny reservoir symbol internal to the schematic symbol of a device employing a drain line. Connected fluid conductors are indicated with a dot at the intersection. Unconnected fluid conductors do not have a dot at the intersection. I find this method a little confusing, so I typically indicate unconnected conductors that simply cross in the schematic using an overpass symbol. You'll appreciate the clarity this modifier provides as our circuits increase in complexity. Since we're on the subject of solid dashed and dotted lines, we may as well discuss enclosures. Enclosures are represented schematically as boxes with alternate dashes and dots, or alternating long dashes and short dashes depending on the manufacturer's preference. An enclosure, as the name implies, is any unified collection of other devices or passages. The classic example of an enclosure is a manifold, which is a machined block of aluminum into which passageways have been drilled. Manifolds save space, reduce the possibility of leaks, and eliminate the need for external piping. Another good example of an enclosure being put to use is a single valve body containing two or more devices. Consider a variable flow control valve with an integrated check valve bypass. Lacking the enclosure symbol could mean that this is composed of two independent devices, a variable flow control valve and a separate check valve that need to be connected together in the proper orientation of function. The enclosure symbol around these two devices makes it painfully obvious that this is really just one device inside the same valve body. Manufacturers may or may not go to the trouble of drawing enclosure symbols around integrated devices. Again, solid lines are working lines, dashed lines are pilot lines, dotted lines are drain lines. These lines carry fluid. Enclosures, in contrast, are not lines that carry fluid, but rather a box housing integrated devices or other lines. Enclosures are represented schematically as alternating dashes and dots. Let's now discuss fluid colors. Schematics sometimes go to the trouble of specifying flow routes through a system at various stages of actuation. Fluids at different pressures or bound to or from certain passages are assigned specific colors. If you've been following this lecture series in its intended sequence, you've already seen me make use of some of these colors. Although I will admit, I'm not as consistent as I'd like to be, since I sometimes use random colors to draw attention to various aspects of a particular schematic. That, and I genuinely detest the color purple. Anyways, red is used to represent fluid at working pressure from a pump to a device. Blue is low pressure return flow. Return flow is ordinarily bound for the tank. Yellow is metered, controlled, or restricted flow. An example of restricted flow would be after a flow control valve or restriction. Orange is pilot or reduced pressure flow. You'd think using the same color for two different flows would be confusing, but it isn't. An example of pilot flow would be to the dashed pilot input of a pilot to open check valve. An example of reduced pressure flow would be the solid outlet of a pressure reducing valve, a common pressure control valve we'll examine in later lectures. Green is suction flow from a reservoir to the input of a pump. Additionally, green is sometimes used to indicate drain flow in a dotted drain line. Again, you'd think this would be confusing, but it isn't. Green suction flow happens only in one place, on a solid line on the inflow of a pump. Green drain flow appears on the dotted lines to the reservoir. Finally, purple is pressure intensified flow in excess of the main relief valve setting due to load-induced conditions or intensifiers. We'll discuss pressure intensification in later lectures. Moving on, let's discuss some common thematic elements found in schematics. First, valves and valve positions, as we learned in the directional control valves lecture, are represented schematically as boxes. Rotary devices like pumps or hydraulic motors are represented schematically, appropriately enough, as a round circle. Fluid conditioning devices like filters or heat exchangers are represented schematically as diamonds. Springs look like springs. If the spring or valve is adjustable, a slanting arrow indicates this feature. That's really about it for general schematic guidelines. Try not to hurt yourself. First, prime movers are devices used to spin the shaft of a pump. Prime movers are devices that convert one form of input into rotational mechanical power. A motor is represented schematically as a circle with an M inside it. A motor converts electrical power into rotational mechanical power. An internal combustion engine, or ICE, is represented schematically as a box inside a box. An ICE converts the stored chemical energy of old dinosaur bones into heat, noise, global conflict, pollution, and rotational mechanical power. Pumps, in contrast, are mechanical power to fluid power converters. A pump is represented schematically as a circle with an arrow pointing away from the pump body in the direction of provided flow. Hydraulic pumps pump liquid from a reservoir, symbolized by an open bathtub-looking thing if the reservoir is vented to atmospheric pressure. If the reservoir is pressurized, the bathtub will have a top. The reservoir, or tank as it is commonly known, is kind of the end and beginning of all fluid flow in a hydraulic system. A number of devices return, drain, or otherwise route fluid to or from the tank. For this reason, a number of tank symbols can be found in a hydraulic circuit to limit the confusion of crossing lines. This doesn't mean that there are multiple tanks. All tank symbols are the same tank. If you think about it, the tank is akin to a ground connection in an electrical circuit. It can be considered a common point of connection for the whole circuit. The shaft linking the pump and prime mover is represented schematically as a bar or a line. The pump isn't ordinarily directly driven by the prime mover, but rather the two shafts are linked via a coupling. The coupling compensates for misalignment and allows a technician to take the pair apart for maintenance and repair purposes. If a pump displaces a fixed quantity of fluid per revolution, no modification is necessary to the schematic symbol. If, however, the pump can vary the quantity of fluid displaced per revolution, a slanting arrow indicates the pump is a variable displacement pump. Since variable displacement pumps have a nasty habit of being nasty, you'll often see a case drain modifier accompanying the schematic symbol. You'll note the dotted drain line routes any fluid leaked out of the pump back to the tank. If a pump includes a vertical arrow on the side, this indicates the pump is pressure compensated, and that flow rate can vary as a function of pressure. We'll discuss these advanced pump features in greater detail in later lectures. However, we should be able to identify them schematically from this point forward. Note that not all pumps are rotary in nature. Consider a manual pump associated with a bottle jack or used as a backup source of pressurized flow. Note that check valves associated with a manual pump suck in fluid on an upstroke and expel fluid on a downstroke. Let's now discuss common actuators. A hydraulic motor is essentially the opposite of a pump. The schematic symbol tells us quite succinctly. A pump converts rotational mechanical power to fluid power. In contrast, a hydraulic motor converts fluid power to rotational mechanical power. Note the arrows of a hydraulic motor point inwards, indicating the hydraulic motor is consuming fluid power, whereas a pump provides it. Given there are two arrows, the schematic symbol also tells us that this particular hydraulic motor is bidirectional in nature and can rotate clockwise or counterclockwise with a given torque and rotational speed, as dictated by the hydraulic system pressure, flow rate, and valve position. Fans of hydraulic motors will be super bummed to be informed that I hate hydraulic motors. Just kidding. I only strongly dislike them, and not nearly with the antipathy I associate with the color purple. I am a loyal fan of electric motors, and other playlists at the Big Bad Tech channel extensively cover these wondrous, powerful, and flexible devices. This being said, hydraulic motors do present certain advantages over electric motors, notably their quasi-instantaneous reversibility and holding power when fluid flow is blocked. This being said, I still don't like them. They're dirty and greasy, and just not as sexy and appealing as an electric motor. While we're on the subject of crushed expectations, hurt feelings, and broken hearts, realize a majority of this playlist covers industrial uses of hydraulics associated with fixed manufacturing applications or renewable energy. If you're looking for information about hydraulic transmissions or automotive applications, look somewhere else because I'm not covering them. While not necessarily the focus of this playlist, I also have a tendency to only casually cover mobile applications like construction equipment. While interesting, these applications aren't the focus of this series. This being said, the base hydraulic principles, devices, and applications I intend to cover are all true and applicable to all circumstances. Long story short, the hydraulic actuator of choice you'll see over and over again in this series is the linear actuating hydraulic cylinder. So it'll be well worth our time to review the collection of cylinder schematics we introduced in the Hydraulic Cylinders lecture, available at the Big Bad Tech channel. Double-acting cylinders have a cap-end port and a rod-end port. The act of extending a double-acting cylinder routes pressurized flow to the cap end and dumps the rod end to tank. In contrast, the act of retracting a double-acting cylinder routes pressurized flow to the rod end and dumps the cap end to tank. Hence the origin of the term double-acting. Rod and cap end serve as both entry and exit points depending upon the action being performed. Single-acting cylinders, in contrast, have only one port and only actively perform one movement. Single-acting cylinders ordinarily rely on a spring or the weight of a lifted object to passively perform the opposite movement. This particular single-acting cylinder is hydraulically extended, spring retracted. The act of extending this type of single-acting cylinder requires pressurized flow to enter the cap end. When the cap end is drained to tank, the spring on the rod end passively retracts the cylinder. In contrast, this particular single-acting cylinder is spring extended, hydraulically retracted. The act of retracting this single-acting cylinder requires pressurized flow to enter the rod end. When the rod end is drained to tank, the spring on the cap end passively extends the cylinder. These types of single-acting cylinders are commonly utilized in fail-safe braking applications. Note, single-acting cylinders sometimes incorporate a drain port on the opposite end to keep this space from being obstructed by any accumulated fluid that happens to leak past the piston. The schematic symbol may or may not indicate this vent port. Single-acting cylinders don't always require a spring to passively perform the opposite action. Consider a ram, basically a single-acting cylinder with a rod so large it has no rod end functional area. To extend a ram, pressurized flow fills the cap end. To retract the ram, the cap end is slowly drained and the weight of the lifted object passively retracts the ram. We'll discuss flow control methods and counterbalance valves in later lectures that allow the controlled descent of a lifted object. To fill out the family tree of cylinders, you should be familiar with the following cousins, nephews, nieces, uncles, aunts, and distant relatives. A double rod cylinder obviously has two rods. Note there is no area nor volume differential between the two rod ends given identical diameter rods. Given these conditions, double rod cylinders can be used to ensure the same force and velocity in either direction. Tandem or duplex cylinders are kind of like back-to-back double-acting cylinders. Tandem cylinders are one permanently affixed entity, whereas duplex cylinders can be taken apart. A telescoping cylinder looks like an old-school pirate spyglass. Intensifiers are something new. They're not really actuators, since there's no rod that interacts with the outside world. They do kind of look and act like a double-acting cylinder, so that's why I put them in this group. Intensifiers are basically a double-acting cylinder, such that a larger piston pushes on a smaller piston. Same force, smaller area. You should know what's happening. We'll examine intensifiers in later lectures. Additionally, you should be able to identify double-acting cylinders with cushion on retraction, cushion on extension, and cushion on extension and retraction. If a cushion includes a slanting arrow, this indicates that it's a variable cushion and the level of cushioning is adjustable. Moving on, let's review the schematic symbols of some basic valves, starting with a pressure relief valve. Pressure relief valves have a pressurized P port and a return port T. A dashed pilot line passage senses pressure on the P input, and a variable adjustment spring adjusts the pressure set point. Pressure relief valves limit maximum pressure by providing an alternate flow path to tank if an actuator stalls out at the limits of travel, a valve closes, or a flow is otherwise blocked. Pressure relief valves are customarily employed between the pump and the tank. Pressure relief valves are often identified on the schematic using the shorthand RV, PRV, or if it must be explicitly stated the relief valve is pilot operated, PORV. The pressure relief valve lecture, available at the Big Bad Tech channel, discusses the pressure relief valve in great detail. Directional control valves are valves that stop, start, or change direction of fluid flow. Directional control valves have a number of identifying characteristics. Positions are particular functions performed by a directional control valve. Ports or ways are the number of ins or outs to the directional control valve. The actuation method is the means the valve is shifted from position to position. Actuation methods include, but are not limited to, manual levers and electrical solenoids. Return springs either offset or center a directional control valve into a particular deactivated position. Modifiers like manual overrides and mechanical detents can change how a directional control valve asserts a particular position. Directional control valves are often referenced on a schematic using the shorthand DCV. If there is more than one directional control valve in a system, they're often assigned additional numeric identifiers, as in DCV1, DCV2, etc. The Directional Control Valve lecture, available at the Big Bad Tech channel, discusses directional control valves in great detail. If you are skilled in the contents of that lecture, as I expect you to be, by all means, pause the lecture and see if you can classify the following directional control valves. If you perform the classification correctly, you should have come up with the following titles. This particular directional control valve is a two-position, two-way, solenoid-actuated directional control valve that is spring offset into the normally closed position. Additionally, it features a manual override. This particular directional control valve is a two-position, three-way, manually actuated directional control valve that is spring offset into a position that dumps actuator port A to tank. This particular directional control valve is a two-position, four-way, double solenoid operated directional control valve that is detented. Such a valve could be used to control a double-acting cylinder that fully extends and retracts. Finally, this last directional control valve is a three-position, four-way, manually actuated directional control valve, spring-centered into a closed center position. When actuated by an operator into the straight-through position, P is routed to A and B is dumped to T. When actuated by an operator into the cross-connect position, P is routed to B and A is dumped to tank. Such a valve could be used to not only extend and retract a double-acting cylinder, but also lock the cylinder in position, even in mid-stroke, with a closed center position. In addition to closed center positions, you should be familiar with tandem, float, and open centers. A tandem center also locks the actuator in position, even in mid-stroke, similar to a closed center position. However, it does not block pump outflow. A float center, in contrast, does not lock the actuator in position, but rather allows it to float freely, hence the name. This allows the actuator to be repositioned by an outside force. Similar to a closed center, a float center blocks pump outflow. Finally, an open center does not lock the actuator in position, but rather allows it to float freely and be repositioned by an outside force. Similar to a tandem center, an open center routes pump outflow to tank, thus saving the pressure relief valve the necessity of being actuated. While we're on the subject of valves that influence the direction of fluid flow, recall that the check valve is a valve that allows free flow in one direction and blocks it in another. Schematically, the free flow direction pushes the ball off the seat. In contrast, the block flow direction pushes the ball onto the seat. Check valves are sometimes referenced on a schematic using the shorthand CV. If there is more than one check valve in a system, they are often assigned an additional numeric identifier, as in CV1, CV2, etc. Pilot to open check valves act just like an ordinary check valve in the absence of a pilot signal. In the absence of a pilot signal, a pilot to open check valve allows free flow in one direction and blocks it in another. In the presence of a pilot signal, a pilot to open check valve, as the name implies, opens and allows free flow in both directions. Pilot to open check valves are schematically identified by having a pilot line that forces the ball off the seat. Pilot to close check valves are just the opposite. Pilot to close check valves act just like ordinary check valves in the absence of a pilot signal. In the absence of a pilot signal, a pilot to close check valve allows free flow in one direction and blocks it in another. In the presence of a pilot signal, a pilot to close check valve, as the name implies, closes and blocks flow in both directions. Pilot to close check valves are schematically identified by having a pilot line that forces the ball to the seat. Finally, restriction or orifice type check valves allow unrestricted flow in one direction and allow regulated amount of restricted flow in the other. Restriction or orifice type check valves are therefore a form of flow control. Restriction or orifice type check valves are schematically identified by having a tiny hole drilled through the ball. The check valve lecture, available at the Big Bad Tech channel, discusses check valves, pilot operated check valves, and restriction type check valves in greater detail. Here's a new valve you might run across in a schematic. This is a manual shutoff valve and is used to isolate, turn off, or drain a system. Manual shutoff valves either use a globe, gate, or ball actuated by a handle. These valves are commonly used to lock out and tag out a system. A whole series of flow control valves exist that all use a common base schematic symbol, that of a narrowing of the passageway. Flow control valves are used to restrict, meter, or otherwise control flow rate to an actuator, thereby directly controlling actuator speed. Flow control valves are sometimes called needle valves for reasons I'll explain in the upcoming flow control valves lecture. Long story short, it's because there's a needle in the path of fluid. Pay attention because this schematic symbol is like a game of add-on at the playground. We'll start slow and steadily increase in complexity till someone breaks an arm. This is a fixed flow control valve. The size of the controlling orifice is non-adjustable. If we add a slanting arrow modifier, this is a variable flow control valve. The size of the controlling orifice is adjustable via an adjustable needle. This is a variable flow control valve with a check valve bypass. The check valve bypass forces the flow control valve to restrict flow in one direction and allows full flow in the opposite direction. You should be able to differentiate between restricted and full flow direction if someone tosses this schematic symbol on your desk. This is a pressure-compensated variable flow control valve with check valve bypass. The vertical arrow modifier lets a technician know that flow rate will remain fixed regardless of applied load conditions, within reason. This is a pressure and temperature compensated variable flow control valve with a check valve bypass. The arrow and thermometer modifier lets a technician know that flow rate will remain fixed regardless of applied load conditions or the temperature of the applied fluid within reason. In summary, the flow control valve family controls the speed of an actuator. In contrast, the pressure control valve family controls the strength of an actuator. These are all new valves we've yet to apply in any of our basic circuits, with the exception of the pressure relief valve. Honestly, it's a little too early to dive into this tar pit, so I'm going to leave a thorough discussion of pressure control valves until later. You'll note all these pressure control valves look astoundingly similar. This being said, there's 5 basic ones, and if you know what you're looking for, they're pretty easy to identify. The characteristics I use to classify them are as follows: pilot line, deactivated state, whether the valve has a check valve bypass or not, whether the drain is internal or external, and most importantly, the location and perceived function of the valve. We'll go over pressure control valves later. However, I am going to breeze through it now since repeat exposure to this topic is pretty helpful. Pressure control valves, since it's implicit in their title, control pressure by monitoring pressure using a dashed pilot port. Most of the times the pilot line is internal to the valve, or it can be an external connection in the case of an unloading valve and certain configurations of counterbalance valves. Regardless, when pressure in the pilot line exceeds the value set using the adjustable spring, the valve actuates into its opposite state. Most of these valves are normally closed that open when pressure exceeds the set value. Pressure-reducing valves are a notable exception because they are normally open, and when pressure exceeds the set value, a pressure-reducing valve would close. That's a dead giveaway. Some of these have check valve bypasses, some of them don't. The ones with check valve bypasses, like sequence valves, counterbalance valves, and pressure-reducing valves, are designed to control pressure in one direction and be bypassed in another. The ones without check valve bypasses, like pressure relief valves and unloading valves, are ordinarily employed in regions with unidirectional flow paths, rendering reverse operation a non-issue. Some of these valves necessitate external drains, some of them don't. The ones with external drains, like sequence and pressure-reducing valves, have pressurized secondary ports. The ones with internal drains, like pressure relief valves, unloading valves, and counterbalance valves, are ordinarily intended to operate with a secondary port at low pressure, rendering an external drain unnecessary. Finally, and most importantly, very often the location and perceived function of a pressure control valve is a dead giveaway about the valve's true nature. Pressure relief valves are always between a pump and a tank. Unloading valves are also known to loiter around the pump. However, they're easily distinguishable from a pressure relief valve since their pilot passage isn't internal to the valve, but rather a remote external connection. Sequence valves are known to hang out around the input of actuators, as do pressure-reducing valves. They're distinguishable from one another since sequence valves are normally closed and pressure-reducing valves are normally open. Finally, counterbalance valves are the opposite. They normally hang out around the output of actuators. Note the terms input and output are relative in nature, especially regarding double-acting cylinders. As we'll learn in later lectures, the check valve bypass allows pressure to be regulated in one direction, yet when flow is reversed, the pressure control valve is bypassed. Note if location and perceived function still doesn't clue you in, sometimes the schematic includes specific port identifiers and goes to the trouble of referencing the valve in the legend. Long story short, anytime one of the pressure control valve quintuplets pop up, you should be able to run through this list and check off as many identifiable characteristics as possible. Sooner or later, you'll hit upon which valve you're looking at. Like I said earlier, don't stress so much about pressure control valves right now. We'll examine each one in greater detail in later lectures. This early exposure to the topic I'm hoping will set you up for success in the future. Alright, let's see. We discussed prime movers, pumps, reservoirs, actuators, directional control valves, check valves, flow control valves, and pressure control valves. Let's move on to accumulators, instruments, fluid conditioning devices, and some other cool new stuff. Accumulators store pressurized fluid for the purposes of maintaining system pressure, absorbing shocks, compensating for thermal expansion and contraction, developing fluid flow, and controlling noise. We'll examine accumulators in detail in later lectures. For now, you should be able to recognize the schematic symbol for an accumulator and differentiate between the different types of accumulators. The general schematic symbol for an accumulator is kind of like an oval-shaped balloon, which if you know how an accumulator works, is kind of an appropriate analogy. A gas-charged or pneumatic accumulator has a clear arrow inside it, indicating the region above the divider is filled with pressurized gas. The region below the divider is reserved for liquid. The schematic symbol kind of illustrates how an accumulator works. The pressurized gas exerts force on the divider, often a diaphragm, bladder, or piston, which exerts force on the confined fluid. Accumulators therefore can pressurize a system without the use of a pump. The good news is the stored energy in an accumulator can be used when a system undergoes an emergency shutdown. The bad news is an accumulator can also be a source of hazardous stored hydraulic energy. Part of proper lockout and tagout procedures often necessitate that accumulators be discharged prior to beginning any work. Any technician working on a system with a charged accumulator runs the risk of being injured or killed by the stored hydraulic energy. Spring-loaded accumulators swap out the gas-charged symbol for a spring. Weighted accumulators swap out the spring symbol for a big block. Given flow rate, pressure, and direction in a hydraulic system must be controlled to perform some task with the required speed, strength, and precision, it helps if these quantities are measured using common instrumentation, switches, and sensors. The schematic symbol for a pressure gauge or manometer is a needle in a dial. If a system includes quick disconnect inspection ports for portable instruments, they're often indicated as check valves. When disconnected, the check valves are closed. When connected, the balls are pushed off their seats and connection allows flow. Pressure switches and sensors also monitor pressure for automatic systems. The schematic symbol for a pressure switch is a box with an input port and a single-pole double-throw transfer switch symbol inside the box. The spring and slanted arrow indicate that the set value is adjustable. Sometimes span, the difference between the set and reset values, is independently adjustable. Given pressure switches are point of interaction between the hydraulic and electrical aspects of an electrically controlled hydraulic system, the same pressure switch will also have an associated electrical schematic symbol. Here's the electrical schematic symbol for a mechanically interlocked pair of single-pole, single-throw pressure switches, one being normally closed, the other being normally open. Alternatively, some pressure switches use single-pole double-throw transfer contacts, with both a normally closed and normally open side being serviced by a single common terminal. Pressure switches are binary in nature in that there are two clear and definite states, either open or closed. Pressure sensors, in contrast, are analog in nature. Pressure sensors measure pressure and output an electrical signal proportional to the measured quantity. Pressure sensors are sometimes indicated schematically as a box with a slash through it that says PT for pressure transducer. The schematic symbol for a flow meter is kind of like a baseball. Flow meters are often direction and orientation dependent. A flow meter intended to be mounted vertically, in to out, won't return a proper reading if it is mounted out to in, on its side, or upside down. Flow meters that are direction and orientation dependent indicate it with an arrow off to the side. Limit switches serve to monitor the physical position of hydraulic actuators. Limit switches come in two notable forms: physical limit switches that must be physically struck to actuate, and magnetic proximity switches that do not require physical contact to actuate. If limit and magnetic proximity switches are employed in a hydraulic schematic, they will most likely use these schematic symbols. This is the one occasion in a hydraulic schematic where diamonds don't mean a fluid conditioning device. The diamond for a magnetic proximity switch means it's a solid-state device composed of no moving parts. Again, given both limit and magnetic proximity switches are point of interaction between the hydraulic and electrical aspects of an electrically controlled system, the same switches will also have an associated electrical schematic symbol. Here's the electrical schematic symbol for a mechanically interlocked pair of single-pole, single-throw limit switches, one being normally closed, the other being normally open. Alternatively, some limit switches use single-pole double-throw transfer contacts, with both the normally closed and normally open side being serviced by a single common terminal. Here's the electrical schematic symbol for a magnetic proximity switch, making use of a single-pole double-throw transfer contact with both a normally closed and normally open side being serviced by a single common terminal. Single-pole double-throw transfer contacts are very common for solid-state devices. Note magnetic proximity switches necessitate additional power connections not explicitly illustrated in the electrical schematic. These power connections power the solid-state detection mechanism necessary for proper operation. Let's move on to fluid conditioning devices. A fluid conditioning apparatus is instantly recognizable because of its distinctive diamond shape. Again, magnetic proximity detectors being the notable exception. The schematic symbol for a filter is a diamond with a porous membrane, which is a dead giveaway to how filters function. Filters remove contaminants from fluid by trapping the contaminants in the porous mesh and letting clean fluid flow out. You'll sometimes see filters with a clogged filter check valve bypass. The check valve bypass circumvents a compromised filter and allows an orderly shutdown of the system to occur. Heat exchangers are also diamond-shaped. Heat exchangers come in two notable forms: heaters and coolers. A heater adds heat. The arrows point into the heat exchanger. A cooler removes heat. The arrows point away from the heat exchanger. Heat exchangers can use different mediums to conduct heat away from or to the fluid they're conditioning. This is a cooler that uses a liquid heat transfer fluid. Note the arrows are filled in. This is a cooler that uses gas as a heat transfer fluid. Note the arrows in a gaseous cooler are clear. Quick note on cooling heat exchangers employing liquid heat transfer fluids. Coolers come in two notable forms: the tube in a shell heat exchanger and the baffle heat exchanger. Regardless of the construction, incoming hot fluid to be conditioned is always routed counter to the flow of the incoming cool heat transfer fluid. Here's why. As the incoming hot fluid to be conditioned makes contact with the heat transfer fluid, it progressively gives up more and more of its heat as it travels the length of the heat exchanger. Outgoing warm heat transfer fluid is still cooler than incoming hot fluid to be conditioned. Similarly, incoming cool heat transfer fluid is still cooler than the warm outgoing fluid to be conditioned. This counterflow arrangement allows the whole length of the heat exchanger to be used to cool the incoming fluid. In regards to prime movers, pumps, reservoirs, relief valves, pressure gauges, and filters, you might commonly find them all packaged together in something known as a hydraulic power unit, or HPU. The HPU is essentially a self-contained common source and destination for all fluid flow for a larger system. An HPU has everything you need except valves and actuators. A valve or collection of valves making use of a manifold can be quickly added onto the HPU and used to control a larger system with its actuators. Finally, here's a super cool device that you might run across, known as a rotational or rotary hydraulic coupling or union. Rotary couplings are used to transfer fluid power between fixed hydraulic power units and actuators that need to rotate. The classic example is between the nacelle of a modern horizontal axis wind turbine and the hydraulic blade pitching mechanisms in the hub. As the rotor, being the connected hub and three blades, spin, the pressure and tank return connections between the fixed HPU and manifold in the nacelle and the rotating system in the hub need to maintain connection with one another, yet not get tangled up. The rotary hydraulic coupling makes this happen. We'll discuss the internal workings of rotary couplings in applications like hydraulically pitched wind turbine blades and rotor brakes in later lectures. For now, you should be able to identify the schematic symbol of a rotary coupling and explain its purpose. Note that rotary couplings are notoriously leaky, so sometimes you'll see a K-strain symbol included in the schematic symbol. Alright, that is about that. Again, most of this material shouldn't have been new to you, but rather a concise review of all things schematic we've thus far discussed. No, I haven't given you all the schematic symbols for every possible device, but I did give you enough to perform the most common tasks. As we examine more material, I'll introduce more devices and their associated schematic symbols in later lectures. In conclusion, this lecture reviewed and introduced schematic symbols for common fluid power devices, including fluid conductors, prime movers, pumps, reservoirs, actuators, directional control valves, check valves, flow control valves, pressure control valves, instrumentation, switches, sensor, fluid conditioning devices, and special purpose ancillary devices like accumulators, intensifiers, manual shutoff valves, manual pumps, and rotary couplings. Additionally, we discussed the advantages and general guidelines about schematics. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource And be sure to check out the Big Bad Tech channel for additional resources and updates.